Hi, my name is Godanti, 13 years old. For this lesson, we'll be continuing on with the techniques of definite integral. For this lesson of the techniques of definite integral, what we'll be having here will be the divergence theorem, or you can call it the Gaussian theorem. There's also other names which I won't be saying. So let's first recap on the previous lesson, a main introduction to the divergence theorem. So a quick summary is and over here in the end this is going to be scalar, where you're going to have and then when you finally hit this inside, what you're going to have would be like this. Okay, so this is what we mainly here said about for the Gaussian theorem. Well, another thing that we have over here is going to be the difference. So over here, what we have for this part, like for this lesson and all, is mainly the differentiation form. We wouldn't be touching up on the integration form. That will be for future lessons. So over here, another thing is that, so what we're going to have is also the definition of differentiation. So the definition of differentiation basically being, now that we are done with introducing with the Gaussian theorem, over here what we're going to have now is the definition of differentiation. Definition of differentiation, you can y prime, fx prime, both can, your choice. So over here, y prime is equals to dy over dx. So what you're going to end up here with is limit delta x approaches to 0. Then after that, what you're going to have here is f delta x plus x minus fx delta x. So over here for this part, well, since you have this, you can find this fx plus delta x, over here what you can do is simply just move this part over here and move this part over here. And then you'll be able to find it, and as the delta x approaches to 0, they'll be equal. So this is what it's going to be like. Like this. Okay, fx plus delta x is equals to fx plus y prime delta x. So now that you have this part over here, what about partial? Partial. Over here you're going to have partial f, partial x, and then for this part now, so you have partial f, partial x. The thing about it is that there will be two components, right? However, since it's partial x, only one of them changes, and this will be the x. So delta x approaches to 0. For fx plus delta x y minus fx y. Then after that, over here the denominator will still be delta x. So now you have this part. Wait, then how are we going to find out this part once again? So what you can have over here would be whoops. Like this, okay? So this is what you're going to have. And another thing to add on is that for the divergence theorem over here, you have many different forms such as basically all of these. But what we're going to do for this lesson is we're going to basically show that this divergent this divergent f dot dv here and this is equal, okay? So now we have this question over here. So we are supposed to show that the loss of fluid per unit volume per unit time in a small parallel pipe having center at p, x, y, z and edges parallel to the coordinate axis and having magnitude delta x, delta y, delta z respectively is given by divergence hence v equals to del dot v when delta x, delta y, delta z approaches to 0. So what you're going to have over here for this part, so this is the model that basically represents here. So give me a second. So what you have here is that, so for this part, this P2, P and P1. So let's first just take the delta y first since it's the longest side. So what you're going to have is A, B, C, D, the surface area over here, and then here you have A prime, B prime, C prime, and D prime. So over here what we have is mainly to study the velocity, and such what we'll have will be the for V. So this part, what would be for velocity times and this area, for this part it will be the flux. But since you have to find loss of fluid over here, you're going to have the flux afterwards minus of the flux that's going in. Basically something like the amount that goes out minus of the amount that goes in. So what we're going to have here is that first of all, for this part, so this P, you can put like P, in the end you're going to have V. Okay, so over here you can straight away put VP1, or you can also put like VYP1. Yeah, that's a lot of subscripts, but you can put it like this, VYP1. And all those. However, how we're going to start is, let's first look at the first half of this, basically P2 to P. So first of all, when it moves from P2 to P, so for this, when you're going to minus, you're going to use VYP is equals to VYP2, and then after that you have to add, because this is only half of this whole thing, you're going to add half partial partial Vy over partial y. And then what you're going to have at the back would be, since you're moving along delta y, you're going to have delta y over here. Okay? So now you have gotten this, but however, we cannot solve it like this. So over here what we'll have to do is, we'll have to have this Vyp2 equals to, Vyp2 will be equals to Vyp minus half partial Vy partial y delta y. So you have found out for the ABCD over here, this part, the velocity over here. Then after that, what you're going to have now is basically the same thing but for P1. The thing is that for P1 over here, it goes from P to P1, right? So since it goes from P to P1, you can just straight away have Vyp1 is equals to Vyp plus half partial Vy partial y delta y. But over here, since you're supposed to find the loss, you're supposed to minus this Vyp2 from the Vyp1. So in order to, which is basically divergence. For this part, what you're going to have is Vyp1 minus Vyp2, and this will be equals to, so these two, the minus of these two will cancel out, while these two, this becomes a positive, and you add them together and you become partial Vy partial y. Then for this part over here, what you're going to do for this part is that, hey, why don't we add the delta x and delta z, since it's basically this whole surface, and this whole surface and the velocity together, you get the flux. So over here you have so now you have gotten this part. This is what it's like for y, but for this part it's only y, right? Which you have this to find the flux. So then similarly, the same applies for the BC C prime B prime to the AD D prime A prime, and the same for AB B prime A prime and DC C prime D prime, which will have Vx P1 minus Vx P2, and after that you have delta y delta z, which is equals to partial Vx partial x delta y delta z, and then after that over here for this part, what you're going to have is Vjp1 minus Vjp2, and after that delta x delta y, and this will be equals to partial Vj partial y partial j, then after that delta j delta x delta y. Now that you have all three of these, why don't we just put them together, and what you're going to have over here would be the divergence. This part will be equals to, so put all three of these together, you add them all together. And what you're going to get over here is that you're going to get this part, right? I'm just going to put them in order. And you realize that these two are basically equal. So over here, for this part, let's not think this as a force. We think this as just a vector over here, and thus it's basically the same case for these two. Okay. So over here, what you have for this part, this will also be equal to the del dot v. So yeah, this will be equal to del dot v, and here you're proven. Okay, so this is basically shown. Well, so a main summary for this lesson is that we proved that these two parts of the divergence theorem or Gaussian theorem, whichever you like to call it, and the two of them are equal, and that over here we studied the velocity and got this result. Okay, alright, so just okay. So now that we're done here, last but not least, thank you for your watching.